So, all right, what I want to do is tell you a boundary condition for the normal magnetic flux density. The way that we're going to do that, excuse me, this mirrors my video, which is great when I am showing you my face, but it is not great when I am trying to write because I can't see what I'm writing. Well, whatever. Okay, so so assume that we have a situation with a boundary between two materials. Up here we've got material 2, down here we've got material 1. They have different values of magnetic permeability. In order to figure this out, we are going to define a small Gaussian surface. It's going to have sides that are perpendicular to the boundary, and then it's going to have a top and bottom that are parallel to the boundary. And it's a cube, it's kind of like that. And right now, okay. We're going to talk only about the normal component of B, right? So surface normal vector is going to point in that direction. Later on, we're going to talk about the tangential components, but you use a different law to derive that one. So if I'm talking about, I'm going to name this B perpendicular like that. B perpendicular is equal to n hat dot B. And I've got B1 in this region and B2 in this region. So when I am doing this integral, the first thing I'm going to do is I'm going to define this height to be as small as possible. I'm going to have my closed surface integral of B dot ds, right? And it's going to be from 0 to delta H in height. Actually, this is a little bit weird. So I'm going to write it as this way. I'm going to write it as separate parts. The top, B dot ds, plus the bottom, B dot ds. And I'm going to have the sides too. So side 1, side 2, side 3, and side 4 on the back. So S1, B dot ds, S2, B dot ds, and so on. But here's the thing. If I take the limit of this thing as my height goes to 0, this height right here, these fluxes, all the sides, go away. So all I care about are the top and the bottom. And on the top, right, the magnetic flux on the top, if I make this small enough so that B2 is constant in that region, I have n hat dot B2. And the flux on the bottom, my surface normal vector on the bottom is pointing in the other direction for this ds. So that's minus n hat dot b1. And I know from Gauss's law that this closed surface integral has to be equal to 0. Excuse me, that closed surface integral, right? So here's the thing. I've already said all the sides are 0. The only non-zero, and the reason the sides are 0 is because I took the limit as the height of my box went to 0. So all I have is the top and the bottom, and the top and the bottom have to cancel out. So I can write this as n hat dot, oh, and this is times the area times the same area. So n hat dot b2 minus b1 has to equal 0 because I never said anything about what this area is. This has to be true for whatever area I choose. And that is only possible if it's true for the vector fields individually. So here's my boundary condition, which I can get from Gauss's law. Oh man. My whiteboard is a little too big for the field of view of my camera, and it is a pain. Okay. So before I go back to talking about ways that you can use magnetic flux, anybody want to ask a question about this? Does it make sense what I mean about boundary conditions?
Could you elaborate a little bit more? I'm still, I kind of get the boundary conditions, but uh, just one more time to reinforce it, please.
Okay. So boundary conditions become important when you are talking about having two different materials. So like, let's say I have a wire. I'll just draw a little tiny wire right here. And my wire is surrounded by air, mostly, except for right here in this region where it passes through some sort of magnetic material. What I want to know is what is the magnetic field here? So like what's H and B here? What's H and B here? And what are H and B here? They're different. How are they different? They're different based on how these boundary conditions tell us. So this wire in particular is going to produce magnetic fields that circulate around it into and out of the board. So there isn't actually going to be a normal component of the magnetic field in this material because it's all going to be tangential to the boundary right here and right here. What if I had a wire carrying current and laying on top of a magnetic material? Well, then I would have a normal component, and I could say this relationship between the B field. And since there are different values of mu up here and down here, that would tell me that that like H in the top area is not the same as H in the bottom area. Does that sort of clarify it?
Yeah. So then, in the case where there's magnetic material parallel to the wire, the field would prioritize the magnetic material over the open air, correct?
Yeah, because it'll say, well, these magnetic flux densities have to be equal, right? So if like mu2 is larger than mu1, then we have to say that B2 is equal to B1, but H is B divided by mu. So like B2 will actually be H2 will be smaller than H1, even though the B's are equal.
Okay. That makes a lot of sense. Thank you.
And the same thing happens when you're talking about dielectrics, right? I'm getting a little bit off topic here, but that's okay. I think we'll still have time for everything. Imagine you have a capacitor. I'm at a weird angle. if I have a capacitor that is filled with two different materials, like up here I have epsilon 1, and down here I have epsilon 2. There you go. This is a parallel plate capacitor, and imagine that the plates are big enough that I can still say that the electric field inside is uniform and points like this, right? From my plus charges to my minus charges. That's great. But I know that my electric flux density is epsilon E. So like if epsilon 1 is larger than epsilon 2, that means that D1 is greater than D2. Which if you think about Gauss's law, right, the enclosed charge is the closed surface integral of D dot ds. So if D1 is larger than D2, that means I have more charge on the top plate than I do on the bottom plate. That's the kind of thing that can happen. Does that make sense? Because again, because of Gauss's law, we have to have, actually with, for Gauss's law for electric fields, you find that the difference between the normal components of the electric flux densities is equal to the surface charge density. So you can only have a surface charge density on something that's conductive. So if these are perfect non-conductive dielectrics at the interface, there is no charge density. And then you have the same thing where the normal components of these electric flux densities have to be equal. And then that's how you end up with a different amount of charge on the two plates because there are two different epsilon values there. Does that make sense?
So even if you charge one plate and you expect like the other plate to kind of have a similar but opposite charge, it's not going to reach that same magnitude because of the permeability in the middle.
Permittivity. Epsilon is
Permittivity.
permittivity, yeah. Because there are two different values of permittivity here.
Yeah.
This is actually, when you work this out, this is the same as a problem with two different capacitors. Like you can have one capacitor with epsilon 1 in series with another capacitor with epsilon 2. That's the same problem. And then the total voltage is just across both of them. All right, we've gotten way off topic, but I will, we can talk about that more another time.